So I have a collection of 11 data points here, and basically I've got two numbers for each point representing the data. So I've got essentially a time and a weight, and because of that, I'm able to create a scatter plot. My x-axis is how much time has elapsed, so I'm starting at time 0. And my Y value is, I think, weighed in ounces. I can't remember the exact situation here. But what's happening, you can see, is as time is increasing, the weight decreases. And if I look at it, it's a pretty strong, if I was talking about the direction of this data set, it's decreasing, right? As X gets larger, Y gets smaller. So it's decreasing. I could say it's sloping downwards. The shape it definitely looks linear just looking at the data right there. So I would say it's linear. And I would say that it's pretty strongly correlated. If I wanted to calculate the correlation coefficient, I could do that by doing, actually, let me go ahead and create the line of best fit. So I'll just do fit line. And fit line only requires one argument. It requires a list of points. So I'll just hit enter, and the list of points is stored in list 1. So you type fit line in list 1, it generates the line of best fit. This is the equation for that line. You can see it's y is equal to negative 0.52x plus 15.21. So there's my y-intercept at about, that's funny, I put it in between there. It is positive, plus 15.21. So right around here, 15 is 15.21. And as x decreases, it's going down by about a half, a little bit more than a half each time. So that's the line of best fit. I can look at the correlation coefficient by just typing in correlation. And correlation coefficient also requires the list of data, so it's list 1. So when I press enter there, it says my correlation coefficient is 1. That's amazing, because I know it isn't. What's happening in GeoGebra is there's a round off. So if I hit options and go to rounding, I could say, oh, give me 5 decimal places. So my correlation coefficient is very, very strong. So when we talk about the strength of the relationship, if you're very near -1 or very near +1, we say that it's a very strong correlation. Basically, the strongest it could be would be -1 or +1. And as these points kind of diverge from that data set, so for example, if I was to move these away, you can see that the correlation coefficient is decreasing because, and that's all the way down to 0.76, 0.85. So moving these points further away from the line diminishes the correlation coefficient. Also, I could take this and I could pull these so that they start to look like they're aligned with a positive slope. And all of a sudden now you can see now the direction is positive. And as I get these points closer and closer to the line, right, I'm going to move them this way. As I get them closer to the line, the correlation coefficient becomes closer and closer to 1 again. Although right now it's only at 0.59. Am I missing a point? Oh, yeah, there's a point that's off the screen that I'm missing completely. And right there at K, and it's having quite an effect. I was unable to make this data do what I wanted it to do. Okay, so now that I've got that K value in there, I can get these points so that they're very, very close to fitting the line. So now I would say that it's a very strong relationship. However, this time the direction is positive. The correlation is 0.9975, so about 1. The only thing I haven't talked about is residuals. So residuals are the distance that a particular point is from the model that's predicting it. So this line is my linear model, and you can see right here, point E is not being very well served by the model for some reason, right? It's below the line. Now I can create a residual plot and take a look at that. In fact, all you have to do to create a residual plot in GeoGebra is come right down here to the input and type residual. And residual plot needs two things. It needs to know where your data is. Our data is stored in list 1. And it also needs, oops, that was wrong. Shift tab. It's in list number 1. And it also needs to know the function that's modeling the data. And here our function is A. So when I do that, Down below, I have a list of the residuals. And you can see residuals can be positive, right? Positive residuals are above the model. Negative residuals are below it. And you can see I can grab this particular point right here, and as I grab it down, you can see. Now, what's interesting is that moving these points is actually affecting the model. So moving one point actually changes all the residuals slightly. Um, Now, one of the things to look for is when you see in your residuals kind of this kind of clear pattern where you see the data points are like above, yeah, like that. So they're above and below. If I look below here at my residual plot, because I see this kind of pattern like this, probably a linear model is not the best model for this data. There's perhaps something going on here. And I don't know if it's a quadratic equation or this doesn't look like necessarily an exponential function, but those shapes like that in a residual plot indicate something probably is going on. And when you have a small data set like this, you can just kind of see them in the actual plot itself. So anyways, that's basically the gist of most of the data things we've done, right? We know, again, correlation, right now it's pretty small, it's 0.31, so I would say that's weak. The shape, not exactly a line, but I'd say kind of a line might be kind of modeling this data. Direction right now is positive. You can see the slope is 0.203, so as x's are increasing, y's are increasing. And then the residuals, right? Each of these have residuals. In fact, at this point, E has a very, very large residual because you can see this is the point where the model says, if I plug in 4, the model's saying it should be right here, but the point E itself has a value that's way, way up here at 19.52. So that's just the vocabulary and the ideas associated with scatter plots and some data analysis that we've done in Math 1.